Humans absorb the subtle shades of language without thinking twice. We instantly grasp the emotion, context, and intent. But feed that same sentence into a computer, and it sees nothing but a blind wall of data. To process information, a machine needs math. It cannot read the alphabet. Before a computer can even attempt to understand a piece of text, every single word has to be stripped down and converted into numbers. This binary matrix shows the earliest attempt to solve this, a system called one-hot encoding. This method took an entire dictionary and assigned a rigid list of zeros and ones to every single word. So cat becomes 1, 0, 0. Dog becomes 0, 1, 0. The glaring problem is that the system learns absolutely nothing about what those words represent in the real world. You and I know a cat and a dog are animals, but mathematically, this encoding treats them as entirely isolated entities with zero connection. Slapping a static numerical barcode onto a vocabulary list is an easy way to file data away, but it lacks any mechanism for true comprehension. Engineers needed a way to measure utility, which led to a method called TF-IDF, term frequency, inverse document frequency. Instead of just creating simple barcodes, this system mathematically weighs how often a word shows up against how rare it is across all documents. This visualization shows how it works in a resume screening system. If you scan a stack of applications, TF-IDF will notice that filler words like the and are everywhere. It lets them fade into gray. But a specific technical skill, like Python, is rare. The system highlights it as highly valuable. Yet even with this targeted precision, a massive blind spot remains. The computer knows the word Python is important to the recruiter, but it still has no data on what Python actually is. Picking out a valuable keyword makes for a great search engine trick. To build artificial intelligence, engineers had to figure out how to teach machines how complex ideas actually relate to one another. The breakthrough came from a simple linguistic philosophy. A word is understood by the company it keeps. If a machine reads enough sentences, it starts to notice patterns. It sees that the words coffee and tea constantly show up surrounded by the exact same verbs and adjectives. They are poured, they are hot, and they are consumed in the morning. Instead of flat lists, models began translating words into number vectors, plotting them as physical locations on a map. Because coffee and tea share similar contexts, their dots are plotted right next to each other to form a related cluster. A model called Word2Vec mastered this by studying immediate, local surrounding words. It sweeps through sentences, using neighbors to predict a target word, adjusting its map coordinates. Another model, Glove, broadens the lens. It scans statistics across massive text libraries, mapping a vast topography based on worldwide word co-occurrence. By turning language into a physical space, computers finally had a mathematical way to quantify human concepts. Because these ideas are now precise coordinates, engineers discovered they could actually perform math with them. This geometrical layout demonstrates the math perfectly. If you take the vector for king, subtract the vector for man, and add the vector for woman, the resulting distance lands you exactly on the coordinate for queen. But language is constantly evolving. What happens when the model encounters a brand new slang term or a typo that simply doesn't exist on its map? To fix this, an approach called fast text breaks words down into smaller fragments. If it finds a word it has never seen, it looks at the familiar prefixes and suffixes inside it to make an educated guess about where it belongs. These spatial models took the rigid, isolated lists of the past and replaced them with a measurable, navigable topography. Still, systems like Word2Vec and Glove shared a heavy anchor dragging them down. They assign one permanent mathematical location to every single word. Take the word bank. In one sentence, it refers to the muddy edge of a river. In another, it's a towering financial institution where you deposit your paycheck. This map node illustrates the problem. The older models force both distinct definitions into the exact same numerical coordinate. The result is a messy average, and the machine loses the specific context of the sentence entirely. Human language is simply too fluid to be locked into permanent coordinates. To move past these static maps, researchers developed contextual embeddings, the architecture behind modern transformers like BERT and GPT. Under this system, the map is no longer rigid. A word's mathematical position shifts in real time depending entirely on the specific sentence surrounding it. Bank smoothly separates into two distinct locations based on whether it sits near water or money. Early natural language processing asked a very simple question: what is this word? Modern AI asks, what does this word mean in this exact sentence? This transition from rigid binary lists to fluid, contextual-aware mathematical maps provided the framework for machines to navigate the complexity of human language. By mapping how words change depending on their surroundings, AI can finally treat communication as a dynamic, evolving landscape.